Hi, my name is Emmanuel Amaro, and this is the advertisement video for our work. Can farm memory improve job throughput? Why are we interested in farm memory in the first place? We're currently at the confluence of two technological trends, which have caused demand for memory to grow faster than its availability. The first trend is that, in the last few years, the prevalence of in-memory workloads such as machine learning and key-value stores has increased the memory demand in compute clusters. The second one is the end of Moore's law, which has prevented DRAM to become denser and cheaper. In essence, farm memory allows compute servers to access memory that is remote. In this diagram, we can see a traditional rack on the left, where each node has its own CPUs and memory available to execute jobs. On the right, we have a rack with farm memory, where the farm memory node at the top shares its memory with the rest of the nodes through the network. Although farm memory does not reduce the amount of memory required to run jobs, it allows to relax the restriction that memory demands for jobs can only be satisfied locally. The three main questions we try to answer in this work are: how can we make transparent access to farm memory fast? Once we have a transparent mechanism for jobs to use farm memory, how do we decide how much farm memory each job should use? And once we solved 1 and 2, can the use of farm memory result in improved cluster job throughput? We chose a system design that extends the operating system to page swap to farm memory through RDMA. We're not the first to extend swapping to use remote memory like this, but we found that previous systems suffer from poor latency and bandwidth due to the following overheads, which occur in the critical path. Head-of-line blocking, which means that high-priority page reads can be queued behind less important prefetch reads. Interrupt handling during critical page reads, which require a context switch to the interrupt handler to finish reading the critical page. And page reclamation, which refers to spending CPU time performing memory reclamation during page faults. Our system fast swap prevents the key overheads we identified, and as a result, it achieves average farm memory page reads in less than 5 microseconds, enabling applications to transparently access farm memory at 10 gigabit per second with one thread and 25 gigabit per second with 7 threads. Once we have a system that allows individual servers to efficiently and transparently access farm memory, we designed a cluster scheduler to decide how much farm memory each job should use. Our scheduler improves job throughput by leveraging farm memory in order to pack the cluster more densely than it would be possible otherwise. The strategy our scheduler uses is the following. If memory is not the constraining resource to admit more jobs on nodes, our scheduler works as any other scheduler. In other words, we simply beam pack on CPU and memory. When memory becomes the constraining resource, our scheduler begins using farm memory as it shrinks local memory given to executing jobs, and the residuals are placed on farm memory. A key challenge we address is that performance degradation when using farm memory is application dependent. For example, if we shrink by 50% the local memory our Spark page rank job uses, its slowdown is greater than 300%. In contrast, if we do the same for our TensorFlow inception job, its slowdown is 11%. Please see our paper for details into how we address this challenge. Accessing memory that is farther away inevitably takes longer than accessing closer memory. So it's far from clear that using farm memory will lead to improved job throughput. However, in our evaluation, we found that, yes, farm memory can improve job throughput when memory is a constraining resource. Finally, let me give you two key results we discuss in detail in our paper. First, if you take a memory-constrained rack and turn one of the compute servers into a farm memory node, this can provide throughput improvements ranging from 2 to 15%. Note, this doesn't require increasing the memory available in the rack. We simply turned a compute node into a farm memory node that shares its memory with the compute servers. Second, if you add 25% additional memory to a farm memory node, you can expect larger throughput improvements, which ranged from 11 to 34% in the cases we explored. This concludes our advertisement video, but we invite you to come watch our full talk on session 5, which includes more details. Thank you.